Hello, this is Professor Khan, and this is EST-100 Week 2, and we are covering Chapter 2 in the book of uh, Electricity for Refrigeration, Heating, and Air Conditioning. So today we will talk about basic electricity, and I will try to go on the physics that constitute electricity, and I'll assume that you would like to know all the basics of electricity and how does it happen and the physics behind it. So I'll try to elaborate a little bit on what the book has said, and we'll go through the PowerPoint. This PowerPoint is available online as well. Okay, so let me move on. So this is the class concepts or the objectives that we would like to cover. We will explain the relationship between physical objects and electrons. What are electrons and what are atoms and molecules, and how does this relate to electricity? We will also talk about what is electricity. We know what it is in a way, but we would like to go to the intricacies of electricity and how is it generated. Why do we need to understand electricity? For us as technicians, it's very important that we understand what is electricity because we will work with it. We would like to protect ourselves from electrical danger. So it will be good for us to understand what is electricity, how does it get generated, how does it get conducted, and so on. And we'll also explain the four types of electricity generation. Power generation is basically electricity generation, and it's important for us to understand the four types where we can available so far for power generation. And finally, I'll talk about conductors and insulators. What makes a conductor and what makes an insulator. Okay, we'll start a little bit. So this is going really back about atoms. I mean, I'm sure you took some kind of physics in high school. You heard about atoms, and they are the smallest components of any kind of element. Any kind of material is composed of atoms. We are composed of atoms. Atoms makes organic and non-organic material, and every atom has these three major components. Actually, it's four. We got the nucleus. Oh, hold on, sorry. Mess that up. Okay, let me get a pen. So we have the nucleus here, and the nucleus itself has inside of it protons and neutrons. This is the core of any atom in the world. Of course, they vary, but every material is consistent. It consists of atoms. So the protons has positive charge. The neutrons has neutral charge, so-called N, no charge, and the electrons have a negative charge. The protons has a lot of things inside. I mean, I'm sure you heard about the Large Hadron Colliders, where scientists were trying to find out, to go deeper and find what is in the protons. Why they are trying to do that? Because we're always very curious about what makes material. Why do we have iron? Why do we have plastic? Why do we have like organic material? What makes material what they are? And so the protons constitute big large of the mass inside the nucleus. So scientists are trying to find out what's in the protons. So they try to hit, from what I understand, to hit protons together at light speed so they will explode and you can find what's inside them. And they found a lot of stuff. And they were trying to find what gives the atom its gravity and what gives it its component. And again, that's a big, large field of research. For us, we can just like be happy to know that there are protons, there are positive, there are neutrons, and they are neutral, and we have electrons. So what gives the atom its weight? It's the nucleus and the proton. Okay, outside the nucleus, there are orbiting substance here called electrons. Electrons, they have no weight. They're basically charged, and they orbit. Every electron has its own orbit. They orbit around themselves, and they also orbit around the nucleus. If you think about it in a very interesting way, it's kind of like the solar system. Things just orbit around themselves and orbit around the nucleus. And there's a whole field of physics called quantum physics about atoms. So, okay, if you can remember that we have proton and electrons are charges, it's a charge, we're good for now. We are building to understand what is electricity. Moving on. If you ever seen this table, it's called the periodic table of elements. All the elements available here on Earth. They keep discovering new elements, and all these elements are composed of atoms. Every atom has different mass, different nucleus, and different electrons. And they are organized based on the number of electrons in the last orbit. So if you look here, these are probably, they have one electron in the last orbit, and it keeps going up until you go to the carbon atom where it has 4 electrons in the outer orbit. So if we go back in here, this is the orbits. So and you can have more electrons orbiting here and here and here and so forth. So going further, this is the carbon atom here, and again, this is helium and hydrogen. Hydrogen atom is the simplest atom we have, and in the middle here we have metals. Metals have the characteristic of having high density, and they also have loose electrons at the outer orbit. So if we say this has 4 electrons and this has 1, this probably have 2 or 3 depending. And so we look here, we'll see cobalt, iron, and gold is here. So these are all the irons. And if you look here in the bottom, you can see all the metals and alkali materials, and we have noble gases in the end. Okay, so why am I showing you this? Just to show you that all the materials are made out of atoms, and this is all the elements we have, and based on the electrons in every atom, the number of electrons and how many orbits there are, we can have what's called conductivity. And if these electrons are just a charge, it's just a form of energy, somebody thought, why do they bond? Why do element bonds? So when we have more than 2 elements, you'll have a molecule. A molecule, how about that? Molecule, the molecule has more than 1 atom. So the water is, for example, H2O, so it has 2 atoms of hydrogen and 1 oxygen. So that's a molecule, that's not an element. So an element is only 1 component. So, and if we look at O2, for example, if it's is O2 a molecule or a element? It is a molecule because it has 2 oxygen atoms. So if you have more than 1 atom, it is a molecule. And some elements do not exist in nature as atoms. They exist as just a molecule. They have to be bonded, and that's based on their charge and their electrons. Okay, elements, we said they used to be 110 in the periodic table, and now they're 118. Well, scientists keep discovering new elements. Every element has different mass, and we said the mass comes from proton. They have a different charge. The charge is based on electrons and number of electrons. The more electrons we have, the more charge we have, and the ones that actually really matter are the ones on the outer, the further from the nucleus, because they're easy to move and bond and have more freedom to get out of the gravity of the atom. So molecules, we said, they're consistent of more than 1 element. We have, for example, H2O, CFC, which is chlorofluoro carbon, I think, or carbonate, and CHCF. I might be wrong about that, but these are 2 elements that we can find in refrigeration, and water is also a molecule. These are examples of molecules. Okay, hopefully this is kind of makes sense. I'll try to post a video about that also from YouTube. Maybe it will be a little bit clearer, but for our intended and purposes, this is enough. Conduction and insulation. So what makes an element conductive and what makes it an insulator? So conduction is the number of it depends a lot on the number of electrons in the last orbit. Again, if we have this small atom, we have this one orbit, 2, 3, and one more. So this electron here is very far from the nucleus, and based on the mass and the distance from the electron to the nucleus, this electron will be easier to knock out, and that will make the material very conductive, so it can gain energy. So one electron can come over and one can come out, and these are electrons. I'm going to call them E's, so they can come in and out. But for it to, so if we just take an electron out and there's no, so if this atom is in kind of imbalance, so you knock one electron out, you take this one out, and you do not substitute it, the atom will have a positive charge and will be receptive to get another electron in order to become in balance again. So it's all about balance again, and everything in nature is going towards balance. The number of electrons in the outer orbit, that's what I'm referring to here. Silver and copper have only one. They have only one electron in the outer ring, the outer orbit, and they have very decent mass in the middle. So it's really easy for them to lose and gain electron, and also it's easier for them to regain stability because they have really high mass, because they're metals and they have a lot of electrons. So that's what makes an atom a little bit conductive. So if we think of gold, silver, and copper, they are very, very conductive. Talking about insulators. Insulators are different. They have very stable outer ring. So let's look at the carbon atom, for example. This is the nucleus, let's say 1 and 2, for example. And the outside, in the outside orbit, we have 1, 2, 3, 4 electrons. So this is more stable than having only 2 in the outer electron. So it's really harder to knock one of those electrons out. It's going to take a lot of energy to knock it out. It will be knocked out, but it's really a little bit difficult. So insulators usually are carbon based because they're very stable, and this is what it looks like. There's like bonds between atoms in carbon based material where we have 4 bonds. So what are carbon based material? Rubber, plastics, polymers, organic material like wood. Those are very good insulators because again they are carbon based, and carbon is very stable material. So I hope that also makes sense a little bit. Single and double, that's what's in the outside orbit, and again electrons are negative charges. So hopefully you get an idea of what we are trying to do. We're trying to move this energy from one atom to another, and energy is just electron. Electron, we're still, I'm not really sure what is the verdict on electrons. Are they just energy or they have some mass? But from what I know so far, they only pure energy. There is no mass to electrons, and this form of energy will again orbits around itself, and it's what gives the material its conductivity. And what happens when you heat a piece of metal? It starts to glow, right? It becomes kind of first yellow, then white. And what's happening inside that material or element is those electrons, they start orbiting very fast, and by orbiting very fast they gain a lot of energy. If you're putting energy, you're probably making it spin so fast, and as they spin so fast they produce a frequency, and that frequency is transformed into light. So light is also a frequency, but light also have some kind of substance to it. We're not going to talk about that. There are photons that are kind of different, but what's happening is you're vibrating the electrons faster and making them gain more energy in the same material without when you add more energy to the element. Okay, I hope this makes a little bit of sense, and also you can go over the book. They try to explain it also in a different way, so let me know if that makes sense to you. Moving on, again, electrons. We said there's a mass, that's here. There's a charge, this is over here in the outer orbit. The field, this is the field of charge, and this is what you have for electrons spinning around the orbit. If you look at the order of orbits, so this orbit will take 2 electrons. This one will take 18 electrons around it. 32, 32, 18, 8, and 12. So it's very stable in this area. There's a lot of electrons. The outer one is the one that's going to conduct energy. And piece of information: if a material can conduct electricity well, it will conduct heat as well, because both heat and electricity are forms of energy. So energy, if you can get the concept of energy, energy is different than power, but they are used interchangeably. But energy is the movement, the force that moves things, and again, we get energy in the atom, and by heat or by electricity or by any other mean. So the frequency also is the spinning of the electrons. And again, if we heat the material, we'll see the frequency of spinning and the vibration of the electrons going really far. And based on that, we can also do a lot of heat, and also we can emit light by the frequency. And you know, light has a frequency. That's why we have ultraviolet and infrared and so on. Okay, so these are the levels. We don't have to concern ourselves with that. This is a lot of chemistry here, but at least you get the grasp of what is making electricity. Moving on. So the flow of electron, that's what we starting to gain interest, especially for our understanding here. So flow. When something flows, it goes from one area to another. That is flow. That's how we understand things flow. It moves from point A to point B. There's flow. If it goes from A to B and stops, there is no flow. That's just movement. But this is flow. It keeps going. And if it's a flow of water, we'll call it current. And it's a flow of electricity, we'll also call it current. So it requires force just like the flow of water. If we want to make water flow from one place to another, we need some kind of force, whether it's gravity, a pump, elevation, which is also gravity. So you need some kind of force to move that flow. Similarly, you will need force to move electrons through conductors, and that force can be generated by difference in potential. So water goes from high to low. You agree? Electricity also will go between high to low, but that's voltage. So voltage, potential. High, we will have high charge and low charge, and we will move from high charge to low charge. So there's always a flow of that sort. So we'll call this, if this is water, we'll call that electricity. And we have a conductor here, and we have here high charge and low, and we keep moving electrons in one way from high to low. Of course, now there is AC and DC. DC, you have constant flow of electrons going in one way, or you can have AC, which is alternating current, which you will have the flow going as a wave. And we'll talk about that too. So I will say DC is very similar to water flow because it goes in one stream. There is no flow, there is no waves in water. So how the flow can be done electrically through friction. When we have friction, we will knock some electrons out. This force could be chemical, and that's a battery. A battery keeps generating electrical potential, which is also mean voltage, or it could be magnetic or mechanical, and this is how an alternator work or a power generator work. We'll talk about that. Or it could happen by heating dissimilar metals. So far these are the most four dominant ways to generate electricity, to generate flow, to generate current. The whole concept of electricity is about current. It's about the flow of these little charges. It took scientists a long time to figure out a way to utilize this energy. People were obsessed with electricity since they saw the electrical eels, since they saw lightning, since they saw charges and sparks. People were obsessed about that to find what is how to make use out of that and how to tame this kind of power. And Faraday did a lot of discoveries in that, and people followed, and every uh, few years, every decade, something comes up. But the biggest breakthrough happened when Faraday uh, discovered the force and the relationship between copper and steel, and discovered the force between magnetic energy and mechanical energy, and that was what made it very lucrative to generate electricity. Chemical electricity has been discovered in 5,000 years ago in China and ancient Egypt, and that was making batteries using acid and metals, and they realized that they can make flow out of that. Heating the similar metal is very recent. I think the next slides have some kind of elaboration about these methods. They are very, very interesting. Okay, so static electricity is caused by friction. There is no steady flow, and once it's balanced, there is no more flow. Probably you have experience with that when you are in the winter time when the air is dry and you walk over carpet and you're rubbing your feet over the carpet. Charges from the carpet are going through your body. Then you touch the knob and there is a spark. So that's static electricity. Again, your body, let's see, this is me going. Your body becomes, for example, positive charge because you're walking on carpet. You touch the doorknob and your body wants to be balanced, so it will flow. The flow will be from negative to positive. Negative charges from the door and from the room to the doorknob, because it's conductive, will balance your charge, and that's why you have a spark. The spark is a result of the sudden flow of energy. Once it's balanced, there is no more flow. So it's very quick, and it's very useful. We use that for a capacitor, but we don't have any steady flow, so we cannot utilize that form of energy to do work. That's something else we need to talk about. Work. What is work? Doing useful work is to have movement, displacement, and this is how we utilize electricity these days. Either we have to do work either by producing heat out of electricity or producing displacement, as in motors. Okay. Chemical electricity, it's basically how batteries work. We have two electrodes. What is it? What's an electrode? It's two poles. If you ever took apart a battery, there are two electrodes. One is positive, one is negative. So there is two sides. If you look at your car battery, there is two electrodes, two sides. And batteries are always DC current. And electrolytes, we talked about electrolytes last week, and we said it's a substance that ionizes when dissolved in suitable ionizing solvents such as water. So salt in water is electrolytes. Salts, acids, bases, and we looked at the periodic table before, and we said at the each side there is like an acid and base is called alkaline. This is the other side of the periodic table. If you remember, I said here are the metals. So we have here acids, here are based. So those are things that are completely highly conductive. So they do conduct electricity. So when you hear about electrolyte, it's a solution. It could be a paste, and battery it is a paste. If you go to car battery, it's mostly liquid. You have acid inside. Probably if you ever worked with old-fashioned batteries, you see that there's a lot of liquid in it. So a chemical reaction happens between the two substances. Whatever you have here is reacting with whatever is in the side of the battery, and over time, it's time to have the right amount of quantity. They react completely and they produce electricity, then it's gone. And this is the basis of making battery out of a potato or a lemon or what have you. Again, it's limited. Once the reaction is done, it is done. These are the basis of dry cell batteries. So zinc, made out of zinc and sometimes other materials, and they actually manganese dioxide is the paste for the electrolytes, and carbon rod. So we are ionizing carbon and zinc together. If you ever taken apart a battery, you'll see that paste in that composition. The new batteries now, if you have in your cell phone, your computers, they are reversible. What does that mean? They are ion lithium batteries. So you have lithium in it, and basically when they react completely, you get a flow. But when you apply flow to it, the material will decompose to what they used to be. So every time you have a composition, you have a reaction, and then decomposition, you get electricity, then you charge them again, you decompose the material. But over time, there's also something called the cycle losses. Every time you have a byproduct, you don't completely return everything to what it was, and that's calculated over time. So probably your cell phone battery can last you for like a year or two, and they can estimate how many times you can go back and forth between charging and discharging until you run out completely of the battery doesn't hold charge anymore. And again, this is a big field of research where people try to make batteries that last longer and less pollutant to the environment, etc. So this is the basis of batteries, and again, they are DC. This is the battery side. Again, carbon base, rod, electrolyte base, separator between the material because you want them to react when you connect those two parts together, the zinc and carbon. Once these two are connected, we have a complete circuit. This is very important word here. Circuit. A circuit is kind of a complete circuit. It's a circle, and if you have a short, the circuit is not complete, and that's something we have to talk about. If you were to have a flow, you will need to have a complete circuit, and in many times, water flow and electrical flow is compared. So if this is if we were to compare this to water flow, this will be your reservoir of water, and this will be your faucet. So you can draw electricity, water from here into the faucet until you run out of pressure completely. But again, the faucet also had to circulate the water into another location, which is your septic tank. So you have to be a circle. If there is no complete path here for the water, it will leak and it will not come to the faucet. And if there is no pipe all the way to the sewer, the water will go somewhere else in your house. So that's not good. That's kind of equivalent to a shortcut in your circuit. So it will go somewhere, but not where you want it to be. So if we were to compare that to a water flow, you need a septic tank and you need another water tank. So this is your septic tank here. This is your water reservoir, and it will go through the faucet and comes back. I hope this makes a little bit of sense, but the idea is you need a complete circuit for the flow to happen, otherwise it will go somewhere else. So what happens if I have this battery and I don't have complete circuit? Let's say this is cut in here, but it's gonna leak, and it's gonna leak to the air. If it leaks to the air, there is no flow, so there is no current, there is no power. If it leaks, if it touches, like for example, the casing or something conductive or ground, it will work, but it did not go where it's supposed to be. So it's kind of like the water coming from your sink going to your house instead of going to the septic tank. So it will work because there is flow, but not where it's supposed to go. Okay, I hope that makes a lot of sense. Thermoelectric is another form of power generation. It's basically having two metals that are different. One of them is nickel, and sometimes the other one is copper. And when they heat it, miraculously, they generate power. How is that so? So remember when we talked about different metals have different electrons, different density, and we said that when we give the atom energy, the electrons start to vibrate and circle around themselves very quickly. They have different energy. So when they have different energy, that's different voltage, which means different voltage mean different potential, and what's called potential difference. And then if you have high voltage and low voltage, what happens? You're gonna have some kind of current, a potential difference, and that will you will have some kind of potential based on the vibration, and that in this case will produce voltage. However, these things are not really that the amount of voltage you get out of heating two dissimilar metal is not that effective, is not that high, but it's very useful. These are the basis of having the bimeter and thermostat. All thermostat now do not have any more mercury bulbs, or they don't have expanding metal. They use something called thermocouples. Thermocouples is just a wire made out of two, actually it's a cable made of two different wires joined at the tip, and when this tip gets heated they generate a little bit of voltage in here, and that voltage can be measured and can be corresponding to a temperature. So this is the basis of thermocouples, and for us this is very useful because thermocouple give us good way to sense temperature in any place. Again, it's made of different type of alloys. Depends, sometimes it's nickel, sometimes it's copper, and the gauge of the wire does make a difference. There's a lot of science behind it. Again, I'm not gonna get into that. The person who invented his name is Thomas Seebeck. He generate current in conductive material. Even material generate different amount of current, and different current means voltage. So the current is basically the flow of energy inside, and we have different voltage, and those thermocouples have to be calibrated. What does that mean? We have voltage now, so we have to, at every temperature there is voltage. So we measure the voltage, for example, at 0 degree, for example, and we'll say this is 0 degree at 3 volts. For example, okay, let's try it again. So let's say that we have 3 millivolt, and again the voltage is very small. It's like millivolts. We got 3 millivolts at 32 Fahrenheit. Okay, then we got 5 millivolt at 212 Fahrenheit. We keep taking. Why did we use 32 and 212? Is because we know this is the temperature for boiling water and the temperature for freezing water. So these are constant at atmospheric pressure, so we can use that to calibrate. There are more sophisticated ways to calibrate thermocouples, and usually they do not go out of calibration very quickly, and they have improved a lot. So the calibration can tell you at what voltage in between that will correspond to what temperature. Just some kind of information about that. Okay, let's move on. Here's another fun gadget, which is called a thermal pot. A lot of people use that who go camping, and if you see here there are two different metals inside this pot, and it does generate electricity that's enough to charge your phone, and while you cook you can charge your phone basically on this little this voltage, and this is basically just to regulate the voltage so you don't ruin your device. Again, it generates a lot of energy, not a lot, actually small energy, but good enough to charge a phone or small appliance, but not enough to power a house or an AC and so on. Again, the thermocouple function is the voltmeter, where we can measure the voltage between the two similar metals. Electricity through magnetism. That's the most dominant way. This is the fourth way and the most dominant way to generate electricity. Every power plant is using this mean to generate electricity, which is basically transforming kinetic energy into electricity, mechanical energy into electricity. And again, it was the Faraday idea of copper and steel along with movement. And I will post a video regarding this idea and how did it work. And based on that, we have the motor principle. How were we able to use that idea to make a motor? And magnetism plays a big part out of that, and it will be a little bit involved. I will explain a little bit of that when we do the motor section. I will post some video to explain that. But the basic idea is we can, if we move a magnet, we will around a copper tube with the right combination of steel and copper, we will get some kind of current. And if we keep that magnet moving with the right polarity of the magnet, which is north and south, we know that, we will keep getting current. So the movement of the north and south of a magnet in relation to the movement of the power generator will cause you to have a continuous current. So it's like kind of a pump. If you think of a pump, a water pump, you're doing the same thing. You're moving the pump to move the water. This time we're moving and alternating to move the current. So think about it as the pump moves water through the pipe. Same thing, a power generator moves electrons through a conductor. And I will post few videos with some kind of nice illustration so you can understand this concept. So conductor and insulator, we go back to the periodic table. Elements with full last orbit, we said they are insulators. We covered that. Elements with loose electrons in the last orbits are conductors. And we said like gold is the best conductor, but nobody will use that for wires, of course, because it's going to be very expensive. However, your computer, your cell phone, your small electronics that require high conductivity and low resistance will have some gold in them. That's why the CPU is very expensive. Silver is the second, then copper, then aluminum, and comes all other metals. But these are the top four for conductors. Is it the same for heat and electricity? Yes, it is. Gold conduct both heat and electricity very well, and so the other materials. What are metals? Metals are atoms with very high density and good loose electrons in the last orbit that can let electrons flow. What are insulators? Material that are organic based or carbon based that have very stable atoms so they do not conduct. Okay, what about semiconductors? Semiconductors are materials that are also close to the metal part in the periodic table. Basically silicon, mica, or I don't know if mica is even an element, or ceramics. Those materials are very semiconductors. So what does that mean? That means that they do not conduct usually, but once they are exposed to electricity, they become a conductor. And that was the idea that actually led to the breakthrough in silicon and in transistors. So we'll talk about that also a lot. So let's say if this is a piece of silicon, we have current going through it, and regularly there's no conductivity here, it's closed, but once you send a signal to it, some electrons, it becomes a conductor and the flow will go on. So it kind of like it acts like a switch. You have to turn it on by electrifying it to make it a conductor. And that, if you can imagine a little bit, kind of made us use a lot of logic and control over small in a small space and small chip. So those are semiconductors. Is there a perfect insulator? That's an important question. Is there a material completely insulated? No. Every material can conduct at the right voltage. Even rubber, even thick insulators, they're always rated. So do not feel very safe touching a high voltage wire with a glove thinking that it will be okay and it's not going to conduct. So everything is conductive, even air, and you'll see spark jump through air, and that's what happens with like thunderstorms and lightning, and also in spark plugs, and in our case electrodes, you'll see a spark jump from one tip to another through air. So that's important to know. So do not trust things that are insulated. Anything that they are insulated, it always depends on the voltage. So positive and negative charges. So this is the last kind of topic I want to touch base on. I know it's a lot of information, and please try to read the textbook. So we have something called the law of charges. Very simple. Similar charges repel, different or dissimilar charges attract. So positive and positive will repel each other. Positive and negative will attract each other. Probably you've seen that before with magnets. If you put north and north, they will push against each other, and north and south will attract each other. how is that helpful? We use that for the motor principle. We always try to do north and south and keep pushing things. I'm sure you did that at some point where you have a one magnet and you push the other magnet with it. So that kind of helps a little bit. And yeah, I'll show you some. I'll bring some magnets and try to show you how this works. Again, atoms can also lose few electrons in a short period of time, then they gain them back. That's for static electricity. Electrons in the outer orbit are of some material can be easily knocked out of their orbit. That's called free electrons. And conductors and materials with free electrons that can be knocked out easily. Atoms can acquire additional electrons and become negatively charged. So that's you walking over the carpet and gaining a lot of charge or losing a charge. So it could be either positively charged or negatively charged. So in electricity, one atom is charged and there is an unlike charge in the other one. So that's when we have flow. We have what we call electrical potential, high charge and low charge, and one charge will go to the other. So if we have water tank in here, it will flow down to the bottom tank. It's the law of nature. Things go from high potential to low potential, high pressure to low pressure in order to achieve balance. So law of electric charges, like charges repel, unlike charges attract. So I hope you can remember that. It's very important for the motor principle, and it's very important also for static electricity. This is an illustration of the charges. If we have two ping pong balls that negatively charges, they have dissimilar charges that will attract each other, and if we charge them both in negative charge, they will repel also with positive charges. So again, going back to conductors and insulators, conductors material have free electrons available and they can transmit electricity through them. Most metals, again, insulators, we said example of that is glass, rubber, asbestos, what have you. But think about the material. If it's carbon based, probably or most likely they are going to be an insulator. Electric potential, it's basically a name for voltage. It's called voltage. It's also called potential difference, electromotive force. Those are all names for voltage. There are volts, amps, and ohms. Those are three aspects of electric circuit, but they're not the same. So voltage is the same name as potential difference, is the same as electromotive forces. The field of forces is the range where that voltage acts. Electric pressure is also called voltage. So if I were to compare voltage to, again, electrical and water comparison, voltage will be water pressure. Current is flow. Current is the flow. And finally, ohms, which is the resistance here. Resistance, which is ohm, okay, is the pipe size. Sorry, the writing is not that clear, but hopefully you can hear me. So this is the comparison here. So we have high pressure. So let's think of again water pressure in a house. If you have big pipe, you have low resistance and water will go smoothly, and you'll still need some high pressure. Think also of the garden hose. It has high pressure, but if you decrease the resistance, you'll have more pressure and more flow. And for flow, you always need a conductor. In water case, it's pipe. In electricity, it's just a wire. Again, this is a lot of concept. Once we do it, I will keep repeating that with some examples so you can get the gist of it. Okay, moving on. This is the illustration of power generation. So you can have either a source of power. This is a basic electrical circuit. Either you have a generator that actually is moved by rotating equipment. The rotation here can be supplied either by anything that will rotate. It could be a motor, a gasoline motor, diesel motor, wind turbine, water flow, and you will have a flow inside your circuit and you will turn on this light bulb. Or you can have a battery, a DC battery, that will make that flow. So you have also a difference in charge and potential difference inside the circuit. Current flow, again, as we said before, that current is the flow of electrons. So if I ask you what is current, what is electricity, is the flow of electrons. So if you can remember that, that will be great. There's always a flow from the power generator, and there's also a flow from the battery. Direct current is flow in one direction, from positive to negative. Alternating current, we have a wave. So if this is DC, going from one direction, from negative to positive, we have small little charges of current. If this is AC, alternating current, we have a wave. We go back from positive to negative, and we'll spend the whole chapter talking about AC and DC. They all have their advantages and disadvantages, and it's a mean just to transfer current, electrons through the conductor, and it's very, very fascinating. But current is measured in amperes. That's the flow. The speed of the electricity is measured in amperes, and that's called a flow. So voltage is in volts, and that is the electric difference. And this is really bad handwriting, I'm sorry. And amps is flow, and measures in amperes. And it was named after Henry Ampere, and voltage was named after Nikola Volta. Resistance, again, it's whatever is opposing your flow. So that's what we need, right? That's what we are using. A heater, an AC, that's your resistance. So you have a flow, the flow is going in its own way, but the resistance opposed, because we're trying to use this energy, right? So if you are using light bulb, you are opposing the flow, and you are taking some of that energy. You are using some amps and some voltage. So you have a good flow, and you take some out of it in here. So you can imagine if you put another one here, another one here, another one here, you have used up the entire flow. At the end here, you end up with nothing. It's kind of like you have a water faucet here. If you open this one completely full, this one probably will get a little bit less in here, a little bit less in here, and finally you have no flow at the end. So again, it's complete flow, and you are using it along the way. And electricity, this flow and this consumption of electricity or resistance is measured in ohms. So high ohms will consume more amps, more flow. Makes sense? Big faucet will consume more water. Okay. This is all I have for this week for the PowerPoint. This card. And I would like to go